Hey guys, we're going to talk about gyroscopes just really quickly to kind of cap off our discussion about angular momentum because, man, gyroscopes are cool. But we'll talk about gyroscopes, not the usual ones you see, but ones that look more like tops right now. So you guys ever had a dreidel before? Or a spinning top? So a lot of times what you do is here's an axis of rotation and you'll spin a top around that axis, and you'll see the top. It'll kind of, as it's spinning, it'll kind of process around, and we're going to talk about that motion. But first, before we do, we're going to look at the case where right now I am not spinning the top, or gyroscope if you want. And so nothing is spinning, and I'm going to go ahead and mark an axis of rotation right here for torques, not for spinning. So right now I'm going to think about the torques acting on my system, and I'm going to draw all my forces, and I'm going to have a normal force. Oops, that's a little too big. I'm going to have a normal force, and then gravity is going to act, wherever the center of mass is on this thing. I think it's pretty symmetric around its width, but maybe a little bit more towards the top of the top. Anyhow, there's gravity. And so right away when I think about the net torque acting on the system, I know that I could have a torque from normal and a torque from gravity. And that would be the net torque. Normal torque does not contribute. Do you know why? Right, because its R value is 0. Right, it's acting at the axis of rotation that I have here. R value is 0, so then I'm going to think about gravity, and I can see that without question there is going to be a component of gravity that's perpendicular, because look, gravity can be broken up into two forces, this and this. This would be the perpendicular component, and this would be the parallel component to the R vector, which of course doesn't contribute. So there will be a net torque from gravity, and this just causes a rotation like this. So this rotation, due to the net torque, will rotate in the counterclockwise direction, which is the positive z-hat direction, or out of the board. And so you can think about right now a rotation that occurs due to that torque. If it starts from us, you can think about an omega, and the omega is going to be pointing right out of the board at you. Right now the top isn't spinning, so all that happens is if you take a top without it spinning, it's just going to rotate and fall down to the ground. So consider now if it is spinning. And so what I'm going to do is to allow it to spin around this axis of rotation here. And I'm going to say it's spinning with some omega like this around that point. And actually, I should really write that as the magnitude of omega. The omega vector itself would be pointing like this. So it points along the axis of rotation, and the actual omega vector would be something like this. Now let's take a look at what the torque is doing. There's still a torque acting on the system with respect to another axis, right? An axis of rotation through here. We're still talking about there exists some kind of perpendicular component of gravity. Here's regular gravity, but there's still a component of gravity like this one. Drew it in a different color this time. Let me change that. There'll be an R vector and a perpendicular component to gravity that causes a rotation. And that net torque from gravity is still pointing in the positive z-hat direction, or out of the board. This means that the angular momentum from the torque of gravity points in the positive z-hat direction, because for a rotating rigid body, of course, angular momentum is I omega. So just like before, there's an omega pointing out of the board. And if I thought about angular momentum, I would realize, of course, there's an angular momentum pointing out of the board. And the change in angular momentum specifically, which is the sum of torques, points out of the board. So what I actually care about is this. When it is spinning, I have an L equals I omega just from the spinning itself. And then from the torque associated with the torque from gravity, there's a change in omega that's going to point out of the board. So I have an existing omega like this, and then the torque changes it, pointing out of the board. Now, instead of causing it to rotate down like this, what it actually does is just causes L to change its direction. Maybe there's a better way for me to draw this, but what ends up happening is this thing will precess around. At some point, L will be here, and gravity will be forcing, when it's in this position, dl dt from its torque that it's created. It'll be forcing it to go into the board at this point. Maybe it's better to look here on a side view. So this is at some point along the precession. This would be my original blue L vector. And right now, the torque, when it was in this position as it precesses around, would be causing a, I'm going to get rid of all the rest of this so I can see it really quickly. It would be causing a dl dt this way. So here, dl dt is out of the board. Here, dl dt looks like it's in the positive x hat. And if I was on this side, again, then dl dt would be into the board. And what's really happening is dl dt is pointing radially. So one way that we can see that is just by observing the precession, that if I have an existing angular momentum vector, that in order for it to precess, it has to change the angular momentum. It changes its direction, not its magnitude. And so you can observe that angular momentum, let's just say in this part, due to just the spinning nature, will have a component in the positive y hat and a component in the positive radial direction. I know it's radial because if I was on this side, the radial direction, here it is still radially outward. Here it's radially outward. And if I think about dl dt, L would have some component in the y hat plus some component in the radial direction. And so I take a time derivative of both of them. The magnitude of L would be constant due to the spin, constant spin. But so this component here would probably be a constant, but what's not a constant is this r hat. So at the end, dl dt will equal 0 plus some stuff that comes out of the derivative times the derivative of the r hat, which is related more or less to the plus or minus theta hat direction. And so you can see that the time rate of change of the direction, here it is, actually produces something in the positive or negative theta hat direction, which in this case, theta hat is out of the board here, it's into the board. This is also the theta hat direction, and you can see that the change in angular momentum due to the torque from gravity, R cross mg, just changes the direction of this bad boy and causes it to precess. So gyroscopes are pretty cool in the fact that when they're not spinning like this, the torque due to gravity will just cause it to rotate, creating an angular momentum out of the board, or more importantly, a change in angular momentum out of the board, because it starts at 0 and ends up at some L. It just causes a rotation like this, but when it's already spinning, all that happens is it changes the direction of the angular momentum and allows it to precess around. So let's look at a couple demos from Tyler. Here he's going to take a big bicycle wheel with an axle through it, spin it for us, and hang it from a rope. Good times.
So for this demo, we're going to be using a bicycle wheel attached to a string. I'm going to get it going quickly with some angular momentum. Put it in the vertical orientation.
So angular momentum while it's spinning is actually pointing along that direction of that axle, right? And then think about what direction the torque from gravity would be acting on this to allow it to precess right now.
And then hold on to the string.
Right, and you see it precessing.
As you can see, it does not automatically fall straight down. That is because the momentum is resisting that torque. As it slows down, it is going to go into its bottom orientation.
So I think it's cool because we can kind of go back and look. And he's spinning this.
Orientation, and then hold on to the string.
Oops.
As you can see, it does.
So as he's spinning it, you see it's spinning around. In this point of view, looking down at it, it looks like it's spinning in a counterclockwise. Well, it's spinning in such a way that the angular momentum vector is pointing at the floor. And if you think about the torque from gravity acting on this, that will be pointing out of the page at you right now, causing a precession in the coming towards you. So think about the direction of the net torque. That's the direction of the change in the angular momentum direction.
Put it in the vertical orientation, and then hold on to the string. As you can see, it does not automatically fall straight down. That is because the momentum is resisting that torque.
Yeah, very
As
cool.
it slows down.
Thank you, Tyler. Let's look at another one. Here's an actual gyroscope, and it's a little bit more complicated, and we have some control of it, but we can watch it precess, and we can also look at secondary precession effects, which have to do with additional torques acting on the system from the location of the masses distributed along its axle. So we're not going to go into that too much, but I still think it's cool to see.
So now we're going to go into precessional effects.
An actual gyroscope.
So on this gyroscope, I'm going to increase the spinning of this large disc, and note it has adjustable masses on the front. As I let it go, I'm getting a precession in one axis and a precession in a different axis.
Pretty cool.
And that is due to the masses and where they are placed.
Okay, so I did just want to talk about gyroscopes really quickly, just so we can have that. It's a really cool effect of angular momentum, and I guess that's it for chapter 11. I guess that's it for the class. All right, you guys, thanks for sticking in there, and I will, be seeing you tomorrow. All right, I'll post this soon. Bye.